Hello everyone, my name is Djilani Kobibi Youcef Islam. I am a professor at Mustafa Istanbuli University of Mascara, Algeria, and I am one of the co-authors of this research paper. I've been researching and working in the field of HVDC and renewable energy systems for over 10 years. Today, I'm thrilled to share with you the groundbreaking insight into the dynamic performance of high voltage direct current systems specifically tailored for offshore wind farms. Our presentation today is all about understanding how we can enhance the performance and efficiency of offshore wind energy. We'll focus on high voltage direct current systems, which play a pivotal role in transmission this energy from high seas to our cities. We will also explore the cutting-edge technology of modular multi-level MMCs converters and their contribution to the field. So here what you can expect from our presentation. First we will start with the introduction, and then the literature review, and then the control strategy, and then the simulation and results, and finally we conclude our work with some conclusions. So the modular multi-level converter MMC, which is the foundation of voltage source converter VSC, high voltage direct current HVDC, has received significant attention over the past 10 years. As a result, the MMC has undergone extensive technical and operational improvements, making it an appealing option for achieving efficient renewable energy harvesting, particularly for offshore wind farms. This paper discusses the state-of-the-art control algorithms that are most effective for simulating large HVDC systems, including offshore wind farms. Moreover, a test system is suggested to show how well the selected techniques perform in practical scenarios. Overall, these works will serve as a helpful shortcut to relevant material that pertains to this research topic. Due to the increased awareness of climate change and falling technology costs, renewable energies have received significant attention over the past few decades. As a result, they have undergone significant improvement. This increase in adoption has led to new challenges in power system operation, owing to the intermittent nature of renewable energy generation, particularly from wind and solar or photovoltaics. A stronger wind velocity profile at offshore farms help them produce more electricity, which is another reason why wind power plants have the greatest growth when compared to other renewable energies. So, we start by describing the HVDC systems. There are two converter types used in HVDC transmission system: the line commutated converters and the voltage source converters VSC, the LCC and the VSC. Let's start with the HVDC LCC, which stands for Line Commutated Converter. This technology has been a cornerstone in HVDC system for many years. It operates by converting alternating current AC to direct current DC and vice versa using thyristors. HVDC LCC systems are known for their reliability and robustness. They have been widely used for long-distance power transmission, interconnection between asynchronous AC grids, and other applications. HVDC LCC systems are like the workhorses of the HVDC world. On the other hand, we have the HVDC VSC, which stands for Voltage Source Converter. This technology, based on semiconductors, allows for bidirectional power flow and offers advanced control capabilities. HVDC VSC is a relatively newer entrant into the HVDC world, but it brings flexibility and precision to the table. HVDC VSC systems are known for their controllability and are well suited for applications that require rapid response to dynamic grid conditions, such as offshore wind farms. The key to the HVDC VSC is its ability to control the voltage and frequency of the AC grids it connects to. So, The HVDC VSC systems represents a solution to many drawbacks of the LCC HVDC, such as commutation failures, interconnection with lower AC system, harmonics, and reactive power. The modular multi-level converter MMC brings the VSC HVDC transmission system to a higher level thanks to such features as scalable modularity for higher voltages, low switching losses, low transient peak voltages, and lower harmonics content, which represent a high quality AC voltages. This topology boasts better balancing capability than conventional voltage source converters, owing to the redundant combination of module connection for each required AC level. It enhances unbalanced operation performance, improves symmetrical AC faults, and considerably lowers the probability of device and system failure. The doubly fed induction generator wind turbine has dominated the market for variable speed technology for models over 1.5 megawatts. The stator windings are coupled directly to the AC grid across the turbine transformer, whereas the rotor windings are connected to the grid via slip rings and a back-to-back voltage source converter, as shown on the figure on the left. In comparison to fixed-speed wind turbines, variable speed operation made possible by the back-to-back converter and rotor blade pitch control results in improved efficiency and higher energy yields. The back-to-back converter enables the wind turbine to operate at variable speeds by partially separating the mechanical and electrical frequencies of the rotor. The primary variables that need to be controlled in the wind turbine generator are the rotor speed, the reactive power, the DC voltage of the back-to-back converter, and the reactive power of the grid-side converter. The figure on the right displays a schematic diagram of the doubly fed induction generator wind turbines control loops. Both converter controllers employs a feed-forward coupled current control, the same as a receiving end converter of the VSC HVDC. The pitch control pitches the rotor blades to minimize the mechanical torque and restore the generator rated speeds when the wind speed exceeds its normal value. Three stages of a modular N+1 level converter with N cells in each arms are depicted on the figure on the left. In order to produce a multi-layer voltage waveform at the converter terminal, this converter depends on the cell capacitor. Hundreds of cells are often required to build a single valve for DC transmission requirements. As the level count increases, the quality of the AC voltage waveform and the harmonic content both declines. Low dV on DT switching times and less voltage stress on the insulation for the interface transformers are produced by small voltage steps and a large number of submodules. As a result, it is not necessary to tolerate the DC link voltage or harmonic current when using ordinary transformers. Furthermore, switching losses and harmonics distortion are reduced as a consequence of the low effective switching frequency per device. Because it is of the VSC types, the MMC topology requires an upper level control more so than the preceding generation. Additional controllers are needed to govern internal variables, lower level control. Now, the phase arms of the converter have series reactors built into them that regulates power flow and circulating currents, and each submodule contains DC capacitors. Controlling these variables and injecting the modulation calls for the use of balancing control algorithm BCA. The figure on the right depicts a high-level representation of the control structure. The upper-level control block typically employs power angle and vector current controls. Power angle control, also known as VF control, is utilized when the VSC converter is linked to an AC system with a passive load or for wind turbine applications. While the reactive power is regulated by modifying the VSC voltage magnitude, the active power is controlled by adjusting the phase angle shift between the VSC and the AC system. The EMTP RV environment was selected to simulate the HVDC system of the figure, which is based on the switching function model and the nearest level control strategy. The simulated test cases assess the dynamic performance of the overall system of this figure under various scenarios, including power flow operation and control strategy. Several simulations were carried out to understand the operation of the previously discussed MMC converter-based wind power evacuation system. The dynamic performance of the transmission system was verified by simulating the normal operation of the HVDC connection of offshore wind farms to the transmission systems, and by simulating the dynamic responses to step change applied to the reactive power regulator and DC voltage regulator at the second modular multi-level converter. The active power produced by wind farm is 666 times 1.5 megawatt and exported from MMC1, an offshore station, to MMC2, an offshore station, as shown on the previous figure. During the 3-second simulation interval, the power reference at MMC1 is set to -1 per unit. The DC voltage is adjusted to 640 kilovolt, and the MMC2 operates at unity power factor. The simulation adopts the constant active power and constant reactive power modes. The active power setting for MMC1 rectifier is 1000 megawatt, and for the MMC2 is 1000 megawatt. The MMC1 operates in VACF control and continuous AC voltage mode inverter. The reactive power is maintained at 0 megavar in MMC2. Initial settings for the offshore converter are for it to operate at maximum active power and absorb 150 megawatt. The figure on the left demonstrates that the converter can meet the required reactive power demands specified in the grid code, and that the MMC HVDC link can respond to the power demand of the wind farm, leading and lagging power factor of 0.95. Only the average capacitor voltage of each arm is represented for clarity in the figures on the middle. I mean to illustrate the capacitor voltage of the phase of submodule of MMC1 and MMC2, which are kept balanced at their nominal values. The voltage imbalances within the converter's arm phases, upper and lower arm, lead to circulating currents with the second harmonic component. Thus, the phase voltages at the PCC for the onshore network and the offshore network are shown to be almost sinusoidal and as such have a small harmonic content. This causes the submodule capacitor voltages to ripple more and distort the arm current as well. The circulating current can be stopped by placing a parallel capacitor resonant filter between the midpoint and of the upper and lower arm inductances on each phase, or by actively controlling the AC voltage reference. Smooth and stable DC voltages are therefore present. Two test cases were examined to assess the dynamic responses of the MMC regulator. The reactive power order of the MMC station 2 rose from 0 per unit to 0.1 per unit at t equal 2 seconds. Onshore station. A sign of good tracking accuracy, the decoupling of the actual and the active and reactive power control loops is confirmed by the fact that it is accomplished in 80 milliseconds without compromising the active power, as illustrated in the figures on the right. Reactive power flow in each AC network can typically be separately controlled, and the active power control is also independent. The next figure describes the response of the onshore MMC to a sudden drop in DC voltage order from 1 to 0.5 per unit at t equal 2 seconds. It is accomplished without impacting reactive power in 50 milliseconds. The active power experienced a transient due to the step change. It can also be observed from this figure that the capacities of the arm remained balanced despite the decrease in the reference value to 0.9 by virtue of direct relationship between the active power and the DC voltage. To evaluate the performance of the control system in both normal and dynamic operation, the two scenarios were tested through simulation. In the normal simulation, the offshore wind turbine generated power will be efficiently transported to the onshore via HVDC link. The step change simulation of the dynamic state helped to reveal the tracking accuracy and assess the decoupled control of the active and the reactive power and DC voltage. This study carries out various simulations to evaluate the steady state and dynamic performance of the MMC HVDC link model and present the MMC control system and the component of the MMC based HVDC. The simulation results are consistent with the control theory outlined above. The link's capacity to react to reactive power demand was examined using the proposed models. The outcomes demonstrate that the models may satisfy the reactive power requirements. Likewise, compared to the multi-level and multi-module VSC arrangement, the MMC inherent scalability makes it considerably more intriguing option for HVDC system application. The performance in an unbalanced grid condition as well as under single and three-phase faults will be the subject of further studies. And thank you for your attention.